Good morning. So, today we are going to discuss about the parameter estimation of the probability density functions, and the particular type of estimation technique that we will discuss is called maximum likelihood estimation. So, till now what we have discussed is we have talked about the discriminant functions for different classes, and we have seen that the type of discriminant function which is very popular is nothing but the logarithmic function of the probability density function. So, when we take any particular probability density function, the probability density function is specified by a number of parameters. So, in particular what we have taken is the normal or Gaussian distribution, and in case of normal or Gaussian distribution, we have said that there are two parameters which uniquely identifies this PDF. One of them is the mean vector and other one is the covariance matrix. So, these are the parameters, that is mean vector and covariance matrix. If this is given, you know what is the nature or structure of the probability density function which is involved in that case. And so far what we have discussed is we have taken the logarithm of the probability density function or a combination of it combined with the a priori probability of different classes to give us the discriminant function for different classes. And when we have taken the decision boundary between two different classes, then we have seen that it is nothing but the difference of the discriminant function. And we have also seen that depending upon the nature of these parameter vectors or the nature of the mean vector and the covariance matrix, we can have different types of boundary, the decision boundary between two different classes. We can have linear boundary, we can have a linear boundary which is orthogonal to the line joining the mean vectors. We have got linear boundary, but which is not orthogonal to the line between two mean vectors, and we have also seen that we can also have in general the decision surfaces which are nothing but quadrics in d dimension, where d is the number of components in the feature vector which we use for classification. So, effectively when we design such a kind of classifier, or we want to find out the decision surface between two different classes, the nature of the probability density function is very important, and as such, as the nature of the probability density function is defined by the parameters mu and sigma, that is mean vector and the covariance matrix, we have to accurately estimate the mean vector and the covariance matrix. Given a Gaussian distribution, we know what is the form of the mean and the covariance matrix, but if the probability density function is other than that, other than the Gaussian or normal distribution, in that case we have to find out what is the parameter vector that identifies the probability density function. Okay. So, today what we will be discussing about is a particular technique for parameter vector estimation for a known parametric form of the probability density function. So, the type of estimation techniques that we will discuss about is the maximum likelihood estimation. So, the problem is something like this. Suppose we have got c number of classes. Okay. So, we have c number of classes, and we are assuming that the kind of classification or the kind of learning that we are going to employ is supervised learning. That means, for each of the classes we have a set of samples for which I know that to which of the classes this set of samples belongs. Okay. So, as we are considering that we have c number of classes, so naturally we assume that we have c sets of feature vectors. Okay. And let us represent that c set of feature vectors as feature vectors d1, d2, d3 up to dc, as we have c number of classes. So, we can assume that the set of samples in each of the classes is something like this, that this set of samples are drawn independently according to the probability law P x given omega j. Okay. So, the samples belonging to class D j or belonging to set D j within this set of samples is drawn independently according to the probability law P x given omega j. Okay. And we also assume that this P x given omega j has a known parametric form. Okay. So, in particular this known parametric form, if it is a normal distribution or a Gaussian distribution, then we have said that this known parametric form is uniquely identified, is uniquely defined by the parameters which are mu and sigma, where mu is the mean vector and sigma is the covariance matrix. Okay. So, these are the parameters which are known for normal distribution or Gaussian distribution. Similarly, I can have other types of distributions which are also parametric, but the parameters may be different from this. Okay. So, what I assume there is that the samples in set D j is are drawn independently according to the probability law P x given omega j, where this P x given omega j has a known parametric form. Okay. So, it has a known parametric form. So, in general I can assume that for class omega j, the parameter vector is a vector given by theta j. Okay. So, this is my parametric probability distribution function, probability density function, which has a known parametric form, whether the parameter is given by this parameter vector theta j. So, to write explicitly the dependence of this PDF on this parameter vector theta j, I can write this as P x given omega j theta j. Okay. So, this specifies that the probability density function has the parameter vector theta j. Okay. So, our problem in this case is that we have to use the information available from the samples in the set D j to estimate this parameter vector theta j. Okay. And the kind of technique that we are going to use, we are going to discuss for this estimation of the parameter vector theta j is what is known as maximum likelihood estimate. Okay. So, what you have to do is we have to use information from training samples in set D j to have a good estimate of the parameter vector theta j. Okay. So, while doing so, we also assume that the samples in set D I does not provide any information about the parameter vector theta j. Okay. For I not equal to j. Okay. So, for I not equal to j, samples in D I does not provide any transformation of the parameter vector theta j whenever I is not equal to j. That means, the classes are or the samples belonging to different classes are really independent. So, samples from one class does not provide any information of the parameter vector of the probability density function of another class. Okay. And as we have also assumed that the samples are drawn independently. Okay. So, I can make use of these individual samples to estimate our probability density function, right. And because the samples in d I does not provide any information about the parameter vector theta j. So, effectively what we have is we have C number of independent problems. Okay. So, given a set of samples, I have to estimate the parameter vector of the probability density function, which best estimates the data distribution within that particular set. Okay. So, I can simply get away with these subscripts I and j and all that. I can simply write P x given theta, because I have independent C number of problems. I have a set of samples. For that given set of samples, I have to estimate the parameter vector theta of the probability density function, which best describes the data distribution of that particular set. Okay. So, instead of using these subscripts, I can simply write that I have to estimate P x given theta, where I have been given a set of samples. So, set of samples D, okay, and using the information available in these samples, I have to estimate this particular parameter vector theta, right. And as the samples are drawn independently, and if I assume that D contains n number of samples. Okay.
So, what is P x theta given theta?
See, what I have said is P x given omega j theta j. What is the interpretation of this? This is the probability density function of the set of samples in set D j. I know that the samples in set D j actually belong to class omega j, and theta j is the parameter vector which specifies this probability density function. Okay. And because of our assumption that the samples in D I does not provide any information of theta j. Okay. I have C number of such sets of samples D 1 to D c, as I am considering that I have C number of classes. Okay. And each of these set of samples independently provide me the information of the parameter vector of the corresponding class. D 1 does not give me any information about theta 2. Similarly, D 2 does not give me any information about theta 1. Okay. So, effectively what I have is I have C number of independent problems. Okay. Given a set of samples D, I want to estimate the parameter vector theta of the probability density function, which best describes the data distribution in set D. Okay. So, because the samples in one set is not giving me information about the parameter vector of the other set corresponding to the other set. So, I can simply remove this subscript j, or even I can remove this class conditional probability omega j, because what I have is given a set of samples, I want to estimate the corresponding theta. Okay. So, it is the parameter. It is the parameter vector that describes the probability density function.
It can be like weight vector.
No. Theta j simply tells you what is the shape of the probability density function. Like in case of Gaussian distribution or normal distribution, theta represents the components of mu and the covariance matrix sigma. Is that okay? Similarly, for some other probability density function, the components of theta will be something else, right. Is that clear? So, what I have is, I have a problem that I have set of samples D. I am not bothered about which set it is or from which class the samples has been drawn. I simply have a set of samples D whose distribution is actually specified by the parameter vector theta. Okay. So, instead of this form, that P x given omega j theta j, because now omega j is no more important to me, because I have separate problems. So, I am simply rewriting this in the form P x given theta, right. This theta specifies what is the probability, or what is the nature or shape of the probability density function. Okay. So, given this, if I assume that this D, the set contains n number of samples which are drawn independently. Okay. So, because they are drawn independently, so I can also write from here, what I have to do is, I have to make use of the information available in the set of samples to estimate the value of theta. Okay. So, I can write this, because there are n number of samples. Okay. I can write that P of D given theta in another form. Okay. Theta specifies the parameter vector. So, I can write it in this form, P of x given theta, product of this, let me put a subscript, P of x k given theta, k varying from 1 to n. Okay. Because I have n number of samples in this set D, and the samples are drawn independently. So, this can be written in the product form. Okay. And this term P D given theta, this is what is known as likelihood value of theta. Okay. And the maximum likelihood estimate of theta is the value, say theta hat, which maximizes this function. Okay. So, when this function will be maximized, when actual the set of samples which are drawn and the parameter vector theta, the estimate of the parameter vector which best describes the probability density function or the distribution of the set of samples x k. Okay. So, that time this value will be maximum, and the value theta hat which maximizes this likelihood value of theta, that is called maximum likelihood estimate of this parameter vector theta. Okay. Now, to be more specific, let us have a diagram. Suppose I consider univariate case. This is x, and on this side I plot P x theta. Okay. And I assume that because this is univariate case, I assume that this theta is mu sigma squared, or mu is the mean and sigma square is the variance, right. And suppose I have point distribution something like this, some arbitrary distribution, something like this. Okay. And this theta, the parameter vector, is nothing but mu sigma square, where mu is the mean and sigma square is the variance. Okay. Now, out of this, if I assume that this sigma square is known, I am just simplifying the case. if I assume that sigma square is known, then what is unknown is mu, right. So, from this point distribution, I have to estimate the value of mu. Okay. So, you find that for different values of mu, I can have different types of probability density functions like this p x given theta. When I assume that the value of mu is this, for some other value of mu, the nature of the probability density function will remain the same, but it will shift. Now, why this will remain the same? Because I have assumed that sigma square is known. Okay. So, I can have this different types of distribution functions where the variance value is same, but the mean value is different. Is that okay? Now, you find that all these different distributions, they do not really, all of them does not really represent the distribution of this data set. Only one of them will faithfully represent the distribution of this data set. Okay. So, for that, this likelihood estimate, the likelihood value that p d given theta is very important. Okay. So, if I plot this p d given theta, you find that for different values of x, this p of x k given theta, where theta is nothing but this mu, will have different value. And here for the likelihood value of theta, what I am taking is, I am taking product of all these different values. Okay. So, if I plot similarly, now I plot with respect to theta p of d theta. Okay. You will find that this plot will be something like this. Okay. And this will have a peak at theta is equal to theta hat. And in this case, this will have a peak, because theta is nothing but equal to mu, assuming that sigma square is known. So, it will have a peak at theta equal to mu hat. So, this is what is the maximum likelihood estimate of this p x given theta, which best represents the mean value of this data distribution. Is that okay? So, I have to find out this position of the mean mu hat, or in this case theta hat. Okay. So, this maximum the likelihood value of theta, as we said, is represented by p d theta, which is equal to p of x k given theta, take the product, k is equal to 1 to n, where n is the number of samples present in the set D. Okay. And we have also said earlier that instead of taking this likelihood value, as we have said in case of our discriminating function, that instead of simply taking the probability density function as the discriminating function, if you take the logarithm of it, that helps us in analysis. Okay. So, similarly, here you find that this likelihood value is a product term. So, instead of taking this likelihood value directly, if we take the logarithm of this likelihood value, okay, that is what is the log likelihood. Okay. So, I can define the log likelihood as L theta, which is nothing but log of p d theta, okay, and which will simply be p of d given theta is of this form, which is a product term, When I take the logarithm, it will become a summation term. Okay. So, this will be converted to log of p x k given theta, where k varies from 1 to n. Okay. So, this is the log likelihood. This is the likelihood value of theta, this is the log likelihood value of theta. Okay. And because we are trying to estimate the value of theta, I simply represented this as L of theta, assuming this log likelihood is a function of theta which we are trying to maximize. Okay. And coming to this particular curve, instead of likelihood, if I put log likelihood, the position of the maximum will remain the same, but the curve will be smooth. So, if I plot L of theta versus theta, the position of the maximum will remain the same, but the nature of the curve will be something like this. So, it will be a smooth curve, where this is a sharp curve. And here you find that as we have more and more number of points, this curve will be narrower. As we have more number of points, this curve will be broader. So, that clearly says that if I have a narrower curve, I can estimate the maximum more accurately. Okay. If it becomes a broader curve, then the maximum estimation may not be that accurate, because around maximum I have a flat curve. Over here or over here, if it becomes a broad one, around maximum I will have a flat curve. So, the maximum estimation is not that accurate. And if I have more and more number of points, more and more number of samples, this curve will be more and more narrow, where the confidence in estimating the maximum is much more. If I have very less number of points, then the confidence in estimating the maximum is less. Okay. So, that is what it means.
So, sir, will this theta hat will changes or will remain same?
Pardon?
Will this theta hat
Yeah.
will changes or it remains same as
That is what I said. That depends upon the number of values that I have. Our confidence in estimating theta hat depends upon how many samples I have. If I have more number of samples, my estimation of theta hat is more accurate. If I have less number of samples, the accuracy is not that high. Okay. So, this is what is log likelihood. Whether I use the likelihood value or the log likelihood value, the estimate of theta hat, it will always give me the maximum likelihood estimate, because the logarithm is a monotonic function. Okay. Now, to maximize this, we know that from our school level mathematics that we have to use the concept of differential calculus. Okay. So, what I have to do is, I have to differentiate this L theta and equate that differential to 0, because here theta is a vector. So, instead of simple differentiation, I have to take the gradient. Okay. So, I have to take grad theta, gradient with respect to theta, and if this theta has got say p number of components. So, if theta has got p number of components which are given as theta 1, theta 2 up to say theta p, I put it as transpose because theta is a vector, right. So, if it has got this p number of components, then grad theta operator will be simply del theta 1, del theta 2, del theta p. This is the gradient operator, right. So, what I have to do is, I have to find out the gradient of the likelihood value of theta. That is, I have to find out gradient of L theta, or the gradient has to be with respect to parameter vector theta, and I have to equate this to 0, right. So, when I equate the gradient equal to 0, I get a number of equations, simultaneous equations. I have to solve that set of simultaneous equations, because this gradient has got p number of components. Okay. Because the gradient will have p number of components, and I equate this gradient to 0, that means I will get p number of simultaneous equations. And when I solve this p number of simultaneous equations, I get the components of the parameter vector theta. Okay. So, that is simply what we have done in our school level mathematics. Now, here the problem is, if I equate the gradient to 0 to get a number of simultaneous equations, I may lead to the actual mean or global the global maximum, or I may lead to local maximum. Not only that, simply equating gradient to 0 also may give me the minimum. Okay. So, again you know that if I take the second derivative, that is gradient of gradient, the second derivative will be negative if it is a maximum, the second derivative will be positive if it is a minimum. Okay. So, that way I can filter out which ones represent the maximum values and which ones represent the minimum values. I am interested only in the maximum values. So, I get a set of values of theta which represent maximum. Then for each of them I have to actually find out what is the functional value to identify what is the global maximum. Okay. So, that is what I have to follow to find out the maximum likelihood estimate of a parameter vector. Now, let us say that this one really gives us what we want, that is the validation of your procedure. Okay. So, to validate this, let us take some known cases and let us see that for those known cases whether I get really what I want. Okay. So, for validation I will take the same Gaussian case or the normal distribution, for which I know that the parameter vector which is given by mu, and for simplification instead of taking multivariate Gaussian, let me take the single variate case. Okay. So, the parameter vector is actually given by mu sigma square. And initially for simplicity let me assume that sigma square is known. So, what I have to find out is the mean mu. Okay. So, let us see whether by using this maximum likelihood estimate procedure I really get the mean value or not, given a normal distribution with mean mu and a known variance sigma square. Okay. So, for this Gaussian distribution we know that the log likelihood will be given by ln or the probability density function x k given theta is nothing but minus half this is nothing but sigma square, okay, minus half okay. So, instead of sigma square let me put it as this. Okay. So, this is my logarithm of the probability density function, right. So, what I want to do is I want to differentiate this with respect to theta, and in our case theta is equal to mu, right. So, if I take theta ln p x k given theta, okay, this will be simply, you find that here this term is constant and our variance sigma square is known. So, this term is also known. Okay. So, if I differentiate this term will be equal to 0. Okay. So, what I have to do is I have to simply take the differentiation of this with respect to theta, which is a function of theta. So, if I differentiate this, it will simply become sigma inverse x k minus theta. Okay. And you find that in the log likelihood, I have to take the summation of this for all values for all the samples, that is k equal to 1 to n, and I have to equate that to 0. Okay. So, effectively what I have to have is I have to equate sum of, so let me put this as sum sigma inverse x k minus theta, where k will vary from 1 to n, this should be equal to 0, right. So, from here you find that if I pre-multiply both sides by sigma, that is covariance matrix, right, then what I simply get is summation x k minus theta, where k varies from 1 to n, this will be equal to 0, right. So, this simply gives us that summation of theta is equal to summation of x k, where here also k varies from 1 to n, here also k varies from 1 to n. Okay. What this means is I have to sum theta n number of times, right. So, this is simply n multiplied by theta, because it is the same theta which is being added n number of times, that is equal to sum of x k, k varying from 1 to n. Okay. So, this simply gives us the parameter theta, okay, which is nothing but the maximum likelihood estimate theta hat is equal to 1 upon n sum of x k, k varying from 1 to n, which is nothing but the mean mu. Okay. So, I started with this, assuming the mean is unknown. We have followed the procedure of maximum likelihood estimate of the parameters, and we have really landed to the unknown parameter, which is the arithmetic mean of the set of samples that I have, which is nothing but mean. Okay. Now, let us take the more general case, assuming that neither we know mu nor we know sigma square, that is both mean and variance, both of them are unknown. Okay. So, over here our parameter vector theta is nothing but mu and sigma square. It has two components. Okay. For simplicity, I am considering the univariate case. For multivariate case, the number of operations will be more, that is all, but the procedure will remain the same. Okay. So, here this parameter vector theta has got two components, one is mu, other one is sigma square. So, assume that the first component theta 1 is mu and the second component theta 2 is sigma square. Is that okay? Now, over here the same ln p x k given theta is nothing but half of ln 2 pi theta 2, okay, theta 2 is sigma square, minus 1 upon 2 theta 2 into x k minus theta 1 square, okay, because it is exponential of minus x minus mu square upon 2 sigma square. So, it simply becomes 1 upon 2 theta 2 into x k minus theta 1 square in the logarithmic form, right. So, again if I take the derivative of this with respect to theta, okay. So, grad theta of the logarithmic form L, okay. So, it is nothing but grad theta, sorry, I have not yet come to L because L contains the summation term. So, let me put it as grad theta into P ln P x k given theta. Okay. So, this is nothing but I will have two components. One is derivative of this with respect to theta 1, other one is derivative of this with respect to theta 2. So, when I take the derivative of this with respect to theta 1, you find that this the first component is independent of theta 1. So, this will be equal to 0. So, what I have is the derivative of this with respect to theta 1, and when I take the derivative of this with respect to theta 1, it simply becomes 1 upon theta 2 into x k minus theta 1. Okay. And when I take the derivative of this with respect to theta 2, you find that the derivatives corresponding to both the terms will exist, because in both the places I have theta 1. Okay. And that will simply become 1 upon 2 theta 2 plus x k minus theta 1 square upon 2 theta 2 square. Okay. So, I have to take the summation of this and summation of this over all the samples, that means over k varying from 0 to n, and equate that to 0 to give me the maximum likelihood estimate. Okay. So, what I have is summation of 1 upon theta 2 hat into x k minus theta 1 hat k varying from 1 to n, that should be is equal to 0, one equation, and the second equation will be minus summation of 1 upon 2 theta 2 hat plus summation of x k minus theta 1 hat square upon 2 theta 2 hat square. This should be equal to 0. Okay. So, I have to solve these two simultaneous equations, and when you solve these two simultaneous equations, you will find that you will get answer of the form theta 1 hat is nothing but 1 upon n summation of x k, k varying from 1 to n, okay, and theta 2 hat will be nothing but 1 upon n summation of x k minus theta 1 hat square, where k varies from 1 to n. Okay. So, simply by solving these two equations, I will get these two solutions, right, where you find that this is nothing but mu and this is nothing but sigma square. Okay. So, that validates that when I follow this maximum likelihood estimate, then I really get the parameter vectors which truly represent the set of samples that I have. Then of course, as I said that regarding the accuracy of these parameter vectors that I have to depend upon the number of samples. The more the number of samples I have, more accurate our estimation will be. If I have less number of samples, our estimation will be less accurate. Okay. So, as for accuracy, I have to depend upon the number of samples, I have to have more number of samples, but in most practical cases I do not get sufficient number of samples. Okay. So, as we can't get sufficient number of samples, our parameter estimation may not be sufficient, may not be accurate. Not only that, what kind of distribution it really follows, that is also difficult to predict. I mean, whether it follows Gaussian distribution or it follows exponential distribution, what kind of distribution it follows, that is also sometimes difficult to predict. because we have insufficient number of samples. Okay. So, in such cases, instead of trying for parametric probability distribution, we have a method called non-parametric estimation. Okay. We will discuss that later on, but before that let me just take another example to illustrate how this parameter estimation can be done for arbitrary probability estimation, probability density function. Suppose we have a probability density which is given by, so I will take an example. So, I have P of x given theta, which is given by theta e to the power minus theta x, okay, for x greater than or equal to 0, and this is equal to 0 otherwise. Okay. And suppose again we have k number of samples. So, our problem is to have the best estimate or the maximum likelihood estimate of this parameter theta. Okay. So, I follow the same procedure, that is I find out the likelihood value P d given theta, which is nothing but product of theta e to the power minus theta x k, where k varies from 1 to n. Okay. Once I have this likelihood, I find out what is the log likelihood L theta, okay, which is nothing but logarithm of this. So, logarithm of this will simply be logarithm of this term. So, the product term will be converted into summation term. So, what I will have is sum of ln theta e to the power minus theta x k, okay, where k varies from 1 to n, right. This will simply be sum of ln theta, because here again a product term that will be converted into two summation terms. So, sum of ln theta, where k varies from 1 to n, and as before it is ln theta that will be added n number of times, because it is a constant term that I am adding n number of times. Okay. So, this minus sum of theta x k, where k varies from 1 to n. Okay. So, this I can rewrite in the form. So, here you find that it is theta into x k, sum is taken over k equal to 1 to n. So, I can take out theta outside the summation. So, it simply becomes sum of x k theta into sum of x k, k varying from 1 to n. Okay. So, it will simply be n into ln theta minus theta into sum of x k, where k varies from 1 to n. So, that is my log likelihood L theta. Okay. Next, what I have to do is I have to take the gradient of this. So, I have to find out the gradient of L and equate that to 0. Okay. So, if I take the gradient of L, what do I get? Gradient of this term with respect to theta is nothing but n by theta, because it is log of theta. If I take it if I differentiate this with respect to theta, I get 1 upon theta. Okay. So, this is simply n by theta minus, if I differentiate this term with respect to theta, this theta goes away. So, I simply have summation of x k. Okay. So, it becomes sum of x k, where k varies from 1 to n, right, and I have to equate that to 0, right. So, when you equate this to 0, you simply get n upon theta is equal to x k varying from 1 to n. Okay. So, this simply gives you the maximum likelihood estimate of theta, which is theta hat is nothing but n by sum of x k varying from 1 to n, okay, which is nothing but 1 upon 1 by n sum of x k varying from 1 to n, okay, which is nothing but 1 upon mu, that is the arithmetic mean. Okay. So, this is what is my maximum likelihood estimate if the probability density function is of this form. Okay. So, what we have seen today is that if the probability density function has a known parametric form. So far our assumption is that the PDF has a parametric form or unknown parametric form. That means, I know that what are the parameters, that is what are the parameters which represents that particular probability density function. Now, given that and the set of samples, that is in case of supervised learning, I know the set of samples which are drawn according to that probability law described by that set of parameter vectors. Okay. So, using the information available in this set of samples, how I can best estimate the parameter vector. Okay. And for doing that, what we have done is we have used simply our differential calculus that you have learnt during your school level, that take the gradient, equate the gradient equal to 0, and the value that you get is what is called the maximum likelihood estimate. That means, this is the set of parameters which maximally supports the set of samples which are drawn independently according to the given probability law. Okay. And of course, as I said that the accuracy of this estimation will depend upon the number of samples that you have. Naturally, if I have just 5 samples, I cannot say that these 5 samples will follow Gaussian distribution or normal distribution of a given mean vector and given variance. But if I have say 5,000 samples, I can say that these 5,000 samples, using these 5,000 samples, I can accurately estimate, of course, within some error, I can accurately estimate the value of mean and the value of variance. Okay. So, the accuracy always depends upon the number of samples that I have. More the number of samples, more accurate my estimation will be, and the less the number of samples, less accurate my estimation will be. In some cases, the sample size is so small that I cannot go for parameter estimation at all, or even I do not know what is the parametric form, I cannot even predict what is the parametric form. Okay. So, in such cases, what we have to go for is the non-parametric method. I do not use any parametric probability density function, but given the set of samples, you estimate what is the probability that a sample has some value say x 1, given a distribution of a set of points. Okay. So, we will stop here today, more in the next class. Thank you.